Hi class, this is your lecture for Chapter 8. We are moving on to discuss energy expenditure during rest and physical activity. We are going to be discussing quite a bit of important information within this particular chapter. For any of you guys who are really interested in understanding your total daily energy expenditure, that's actually coming up in the first part of the chapter. We'll talk about how body weight affects the different forms of activity and the energy cost involved. We'll look at the classification systems that rate physical activity intensity. We'll also talk about 2 ways to predict your resting daily energy expenditure. We'll talk about factors affecting walking versus running, and also factors that contribute to lower exercise economy of swimming as compared to running. This is actually a pretty interesting chapter. Lots of discussion is typically facilitated from the information in this chapter. And so we're going to go ahead and jump right into it. So if you've ever been curious as to how many calories your body utilizes in one day, that's what this particular slide is addressing. This is our energy expenditure during rest. It's actually made up of a couple different components. Our resting metabolic rate, our thermogenic effect of food, and the thermogenic effect of physical activity, or number 3, our energy expended during physical activity and recovery. I know this slide is titled Energy Expenditure During Rest. I don't want you guys to get that confused. I think it's more accurately described as the total daily energy expenditure, or the TDEE. And again, that's all of the calories that your body utilizes in the course of 24 hours. So most of the calories that are used for our resting metabolic rate. So processes that occur during sleeping, processes that our organs take in order to be able to perform physiologic functioning, things of that nature. The rest of our energy expenditure comes from how our bodies have to break down and process foods in order to get those nutrients to the cells, but also has to come from a great portion of the physical activity that we perform during the day. And this can be simply just sitting in your office chair. It could be during sport and recreation as well. So how do we figure that out? Well, don't get scared off by these formulas. There are calculations, prediction equations that you can take certain information and plug it into these equations in order to understand how many calories your body utilizes in one day. So this is called estimating your resting daily energy expenditure, and we can do that in a couple different ways. You can calculate metabolic rate by taking into consideration your BMR multiplied by your body surface area. And then once you get that answer, you take that number and you multiply it by 24 because there are 24 hours in a day. Or you could do a resting daily energy expenditure calculation based on being male or female. And then you would put the information in according to body mass, according to your stature and age. The BM stands for weight in kilograms. The stature is for height in centimeters, and then your age is obviously age in years. So if you're curious to calculate what your body burns in one day, you could utilize this formula, and you get a kilocalorie answer in terms of your unit of measurement. I want to stress to you to not get real caught up with these calculations because performing either calculation according to body surface area or simply by using the recommended daily energy expenditure, your resting daily energy expenditure calculation will get you an answer that is very, very similar in nature. Different factors that affect our TDEE has to do with our physical activity. What we do in a day. Are we physically active or are we sedentary? It also has to do with our dietary induced thermogenesis, which means how our bodies take in, absorb, and transport those nutrients for the different metabolic processes that happen over the course of one day. Climate has a lot to do with it. Also, pregnancy has a little bit of factors in regards to your energy expenditure. Specifically with climate, If we have an elevated core temperature, this can produce increased thermogenic effect within the body, mostly because of the additional energy required for sweat gland activity, and it also changes a little bit of our circulatory dynamics as well. And then females, if they are pregnant, maternal cardiovascular dynamics follow normal response patterns. Moderate physical activity presents no greater physiologic stress to the mother than imposed by the additional weight gain and possible encumbrance of fetal tissue. Pregnancy does not compromise the absolute value for aerobic capacity as expressed in liters per minute. As pregnancy progresses, increases in maternal body weight add to the physical activity effort during weight-bearing exercises like walking, jogging, stair climbing, and what you're going to hear of and understand is how this affects the economy of the movement that's required by that individual. So pregnancy, particularly in the last trimester, increases pulmonary ventilation at a given submaximal effort intensity. And progesterone elevation during pregnancy also increases the respiratory center sensitivity to carbon dioxide, which directly stimulates maternal hyperventilation. So that's one way, a couple different ways that pregnancy can affect your daily energy expenditure. All right, let's discuss basal metabolic rate. This is our resting rate. It represents the minimum energy requirement to sustain functions in the waking state. If you're confused by these three different components, I highly suggest you click on first of all, access Blackboard, get into this PowerPoint, and click on these videos that you see here. The third one in particular, I think, is excellent in really breaking down the different components. So it talks specifically about resting metabolic rate. It's a common denominator for expressing basal metabolic rate. Body surface area is a common denominator. Typically, basal metabolic rate is lower in females at all ages, and there are three standardized conditions. When we are measuring BMR, a couple of conditions that are present. First of all, no food is being consumed for a minimum of 12 hours before the measurement, and that's because of the thermogenic effect of food. We don't want them to have worked out for at least 12 hours before, so they need to have that period where they haven't raised or elevated their heart rate. And we also want them to have being laying quietly for about 30 to 60 minutes prior to the assessment in some sort of dimly lit, temperature-controlled, thermoneutral room. Because as we stated earlier, temperature can have an effect on a true caloric value for us in a day. BMR as a function of age and gender also has a lot to do with whether you're male or female. BMR is typically much lower for females than it is for males. And overall, what our bodies require and need on a daily basis as we age in terms of kilocalories actually drops quite significantly. So you can see right here at the beginning of life, starting about age 1, we have a very high basal metabolic rate. Our bodies are functioning, they are processing, probably because of increased growth and tissue repair to create that growth. And so our metabolic rate, the point at which we burn calories, is very, very high. And it remains relatively high, but then it begins to drop off as we hit about age 10. And you can see the rate that it continues to fall at age 20, 30, plateaus a little between the ages of 30 and 40 and 50, and then it begins again to drop off. This is yet another reason why adults suffer from creeping obesity, is we do not have the same basal metabolic rate that we once did when we were in our teens and in our early 20s. And if we continue to consume calories at a very high level, despite the fact that our body no longer requires those calories at a high level, that's where creeping obesity sets in. This slide shows the contribution of the diverse tissues to actually resting metabolism, and you can see how involved the liver is. You'll notice that the liver requires quite a bit of energy for upkeep. Next on the list is a tie between the brain and, the brain and pretty much your skeletal muscle, with your heart requiring very little. When discussing energy expenditure during physical activity, your body size plays an important contributing role to the energy requirements of the activities. Heavier people typically spend more energy to perform the same activity than people who weigh less. So this is why you can have two people on a track. You can have a relatively active individual, doesn't have to be an elite level athlete, but a relatively active individual at the starting line with, let's say, an obese individual. And they will expend, the obese individual will expend more energy to perform the same activity. So you could ask the two participants to do the same type of intensity for the duration of a walk or a run, and the heavier individual will expend more energy performing the same task of the person that actually weigh less. Energy expenditure can be predicted during weight-bearing physical activity from body mass with almost as much accuracy as a lab-measured VO2 max, which is pretty interesting. Two factors affect how researchers rate task difficulty. It's according to duration of effort, also according to the intensity of the effort involved. And both factors can vary considerably. Running a 26-mile marathon at various speeds illustrates this point. One world-class runner maintains maximum pace and completes the race in a little more than 2 hours. Another runner selects a slower, more leisurely pace and completes the run in 3 hours, or let's say even 4 or 5. In these examples, the intensity of physical activity differentiates the performance. In another situation, two people run at the same speed, but one runs twice as long as the other. Here, activity duration differentiates performance. There are several classification systems that rate sustained physical activity for strenuousness. One system recommends classification of work by the ratio of energy required for the task to the resting energy requirement. This employs the physical activity ratio, or the PAR. For example, light work for men elicits an oxygen uptake up to 3 times the resting requirement. Heavy work encompasses physical activity requiring 6 to 8 times resting metabolism, whereas maximal work includes any task that requires metabolism to increase 9 times or more above rest. As a frame of reference, most industrial jobs and household tasks require less than 3 times resting energy expenditure. These work classifications, rated in multiples of resting metabolism, average slightly lower for women because of their general lower aerobic capacity. Work classification based on the PAR model rates the strenuousness of occupational tasks at a somewhat lower level than typical classifications for general physical activity. And this occurs because occupational and industrial work usually extends for much longer durations than does physical activity training, and often requires the use of a smaller muscle mass performed under varying and stressful environmental conditions and physical restraints. Oxygen uptake in kilocalories commonly express differences in a physical activity intensity. As an alternative and convenient way to express intensity classifies physical effort as multiples of resting energy expenditure with a unitless measure. To this end, scientists have developed the concept of metabolic equivalence, otherwise known as METs. And again, this is a convenient way of rating intensity from a resting baseline. Conversions from METs to kcals per minute requires a knowledge of body mass, and the following conversion of 1 kcal per kilogram per hour is equivalent to 1 particular MET. So this is actually very, very common. There's lists out there. If you Googled MET, or if you Googled metabolic equivalent, basically every physical activity known to man, from sitting to chewing to swallowing to brushing your teeth to walking your dog, can be rated according to metabolic equivalence. So look it up. It gets pretty interesting. Some of the activities that they list and the METs associated with it, you're like, wow, I'm not quite sure I really needed to know that using the restroom is the equivalent of one metabolic, one MET. But Google it if you have an opportunity to. It's a level of classification of physical activity based on energy expenditure with corresponding METs. And you actually have a table in your chart, or sorry, in your chapter that give you an idea of associated metabolic equivalents. We can also use heart rate to estimate energy expenditure. For each person, heart rate and oxygen uptake relate linearly throughout a broad range of aerobic physical activity intensities. So by knowing this precise relationship, activity heart rate provides an estimate of VO2 and thus energy expenditure during physical activity. This is the picture that I was referring to a little bit on the last slide. So you can see that they've have the different levels of energy expenditure from light to moderate to very heavy to unduly heavy. They've expressed them according to kcals per minute or liters per minute in terms of oxygen consumption. And again, typically we like to use milliliters per kilograms per minute. So again, you can see the association with that particular level, and then they associate that with METs. So if you're doing something light to moderate activity, typically you might be gardening in your yard, you might be mowing the grass, maybe doing some sort of light walking involved. You can begin to get an idea of the kilocalorie value that's required of that activity and the corresponding metabolic equivalents. So in regards to using heart rate to estimate energy expenditure, you can see on this particular graph here, oxygen uptake is associated with linear increases in heart rate as well. This particular graph shows the linear relationship between heart rate and oxygen uptake for two women collegiate basketball players who had different aerobic fitness levels. The measurements were made during a graded exercise test on a motor-driven treadmill. The heart rate for each woman increased linearly with intensity. A proportionate increase in heart rate accompanied each increase in oxygen uptake. This particular slide looks at the effects of body mass in regards to physical activity. Body size plays an important contributing role in energy requirements, and the picture that you see here illustrates that heavier people expend more energy to perform the same activity than people who weigh less. This occurs because energy expended during weight-bearing activity increases directly with the body mass transported. Such a strong relationship means that one can predict energy expenditure during walking or running from body weight with almost as much accuracy as measuring oxygen uptake under controlled laboratory conditions. In non-weight-bearing activities, such as maybe cycling or stationary cycling, there's a very little relationship that exists between body weight and energy cost. From a practical standpoint, walking and other weight-bearing activities require a substantial calorie burn for heavy people. If you look on table 8.3 in your chapter books on page 233, playing tennis or volleyball requires considerably greater energy expenditure for a person who weighs 83 kilograms than for someone who weighs 62 kilograms. Expressing caloric cost of weight-bearing activity relative to body mass as kilocalories per kilogram of body mass per minute greatly reduces the difference in energy expenditure among individuals of different body weights. Nonetheless, the absolute energy cost of the activity remains greater for the heavier person simply because of the extra body weight. And here's that graph that represents what we just spoke about. So if you look at the activity of volleyball at the top of the chart, you'll see someone that weighs 110 pounds will be expending approximately 2.5 kilocalories versus someone that weighs about 70 pounds greater will expend more calories. So that just goes to show you, ladies and gentlemen, that individuals that carry more weight are having to work harder and are expending more energy to do the exact same activity. And this graph shows us body mass versus stature and energy expenditure, approximate energy expenditures in terms of kcals per day. And you'll notice that the kcals are very different for men versus women. And this is based on gender, age, and then we go off body mass and height as well. So if you don't have access to doing the prediction equations that you were given at the beginning of your chapter, but you simply wanted to ballpark it for, let's say, an athlete or for a client, you could definitely go off this chart if you knew their age, if you knew their body mass in terms of kilograms or pounds, height, and you can see here. So your average high school female that's, let's say, 16 years old, that weighs right around 120 pounds, right, is about 64 inches tall. Usually they're needing to intake no more than 2,200 calories in a day. Remember from some of our previous talks, if you take in more than what your body requires, that would be facilitate weight gain. If you take in less than what your body demands, that would facilitate weight loss. And if you took in exactly that 2,200 kcals in a day that your body requires, that would allow you to maintain your current weight. All right, so the next part is going to be talking about energy expenditure according to modality. So we're comparing walking versus running versus swimming. And a couple things that affect your energy expenditure, what you burn during the different modalities, have to do with the efficiency and the economy of human movement. Efficiency is talking about the minimum expenditure of time and effort, and three factors determine success in aerobic performance. Your aerobic capacity, in other words, what you can consume, what you can expire, the sustained effort at a large percentage of your VO2 max. That's probably meaning that you've got your trained onset of blood lactate to avoid fatigue, and also what affects is your movement economy or your efficiency of your energy use. So think about someone that you've seen before, maybe at the gym, maybe on the sidewalk. They were doing walking versus running, and they just had their arms flapping everywhere. That is a very inefficient movement because you're basically expending energy, extra energy, and not utilizing energy in the best manner in order to be efficient with your movement. So anytime you're trying to be a faster individual, that's why we have athletes that have coaches that specifically work with them on their starts. If you're an athlete that has to start off the blocks, and you're basically hunched over with your hands on the ground and your feet are in the blocks, there's a specific efficiency to the movements of coming up out of those starting blocks. There's a reason why you don't see professional sprinters stand immediately erect out of that position, and it has to do with the efficiency. The minimum expenditure of time and effort in order to really save that energy and to utilize it when it needs to be used. Let's, for example, crossing that finish line after the 100-yard dash or the 100-meter dash. So talking about efficiency of human movement, we need to address mechanical efficiency. And this is described as the percent of total chemical energy expended that contributes to your external work output. So there's two ways that we measure this. We measure the gross versus the net. And this is most affected by energy to overcome friction. So gross mechanical efficiency applies when someone requires specific rates of work and speed that express energy expenditure over extended durations. Net mechanical efficiency is resting energy expenditure subtracted from your total physical activity energy expenditure. And then we have something called delta efficiency, which is the ratio of the difference between work output at two levels of work to differentiate an energy expenditure determined for the two levels of work. So let's kind of clarify that for a second. Each expression, calculated differently, exhibits a particular advantage. Each calculation method assumes a submaximal steady rate condition and requires expression of work output and energy expenditure to be expressed in the same units, which is typically kilocalories. Applying the different calculation methods to the same activity modality yields varying results for mechanical efficiency that range from 8 to 25% using gross calculations, 10 to 30% using net calculations, and then 24 to 35% using delta calculations. Please keep in mind, though, with all machines, the human body's efficiency to produce mechanical work falls considerably below 100%. The energy required to overcome internal and external friction becomes the biggest factor in affecting mechanical efficiency. Overcoming friction represents essentially wasted energy because it accomplishes no external work. Consequently, work input always exceeds work output. There are quite a few factors that influence physical activity efficiency. So all the percentages that were calculated on the previous slide. Work rate is the first thing. As work rate increases, efficiency decreases. A little of that is due to fatigue. Movement speed also. Any deviation from an optimal movement speed also decreases efficiency. Every individual has an optimum speed for movement for any given work rate. And generally, the optimum movement speed increases as power output increases. Any deviation causes a decrease in efficiency. Low efficiency at slow speeds most likely result from inertia. Declines in efficiency at high speeds can result from increases in muscular friction, with resulting increases in internal work and also energy expenditure. There are also extrinsic factors. Improvements in equipment design have increased the efficiency in many physical activities. For example, lighter and softer running shoes with different insole cushioning properties permit running at a given speed with a lower energy expenditure. So we've all seen, the latest and greatest track shoes or the Air Jordans that are coming out, and all of them boast that they have utilized, the most scientific advancements, in their research labs to produce these shoes that should make us jump higher, run further, last longer, so to speak. Another factor that affects is our muscle fiber composition. So remember the type 1 versus type 2 fibers. What sport requires slow twitch muscles versus what sports require fast twitch muscle fibers. So again, if we are athletes that have been trained to be endurance runners, we're not going to be as efficient when we are required to have this, explosive burst of power. Fitness level can also influence physical activity efficiency. More fit individuals perform a given task at a higher efficiency, and that's again because of the opportunity of the human body to adapt to the training that's required. And there's increased circulation, there's better temperature regulation, there's also improved waste product removal from the cells as well. So those are some of those adaptations that take place. Again, body composition. Fatter individuals perform a given task at a lower efficiency, probably because they have more work to be able to produce the same movement. They have more weight to move, and that is science. Technique. Improved technique produces fewer extraneous body movements, resulting in a lower energy expenditure and then a higher efficiency. So a great example of this is the golf swing. Tons of people expend considerable energy trying to direct the ball where they want it to go, most of the time with less than perfect execution. However, our tour golfers seemingly waste very little energy in coordinating the feet, the legs, the hips, the shoulders, the arms, as they strike that ball on the pre-planned trajectory in a precise, coordinated manner. It makes it look effortless. I think that's kind of a sign of an elite level athlete, is that they make it look effortless. How many of us are being overly critical when we watch the Olympics? If you're watching figure skating, and the athlete doesn't hit their triple sow cow, Are we overly critical because they make it look so easy? They have, less extraneous body movements that make it look like a flawless, very simple movement, when in reality it's quite technical. Okay, so the next concept I want to talk about is the economy of human movement. The concept of exercise economy also encompasses the relation between energy input and energy output. For the economy of human movement, the quantity of energy to perform a particular task relative to the quality represents an important concern. In a sense, many of us assess economy by visually comparing the ease of the movement among highly trained athletes. It doesn't require a trained eye to discriminate the ease of effort in comparisons of elite swimmers, skiers, golfers, dancers, gymnasts, with less proficient counterparts who seem to expend considerable wasted energy to perform the same tasks. Anyone who has learned a new sport recalls the difficulties encountered performing basic movements that with proper practice become automatic and indeed effortless. So if you're thinking of the sports gene when you're hearing this particular portion of the lecture, you're right in doing so. This is kind of what Erickson in the 10,000 Hours was touching upon, was the fact that there was meaningful, task-filled, purposeful practice in order to move away from this wasted energy to these effortless movements that look very, very simple in nature when they are quite technical. So the quantity of energy, the movement of economy is the quantity of energy to perform a particular task relative to the performance quality. We typically assess this by measuring steady rate VO2 during a specific activity at a set power or output or speed. At a set submaximal speed of running or cycling or swimming, an individual with greater movement economy consumes less oxygen to perform that particular movement. With all things being considered equal, a training adjustment that improves economy of effort directly translates to improved performance. And this is what can be the difference between an athlete standing on that gold medal podium versus standing on the silver medal or the bronze, or unfortunately not even being on the podium at all. So this is why you'll have athletes that hire coaches just to help them improve their 40-yard dash. You'll have them hire a completely different coach just to help them perform a vertical jump test, because movement economy can make a big difference in regards to improving a performance, because it also has to do with efficiency. So this particular graph shows you the relationship with a submaximal VO2 of someone that's running, 268 meters per minute, and 10-kilometer rate time in elite male runners with the same aerobic capacity. So what you can see here is we've got this race time. As the time increases, the VO2 max, or the VO2, the consumption, actually goes up as well. So this is a perfect example of relating run economy to endurance performance in these elite level athletes who have comparable aerobic fitness. This graph clearly shows that athletes with greater running economies achieve better performance. And keep in mind too, guys, there's no single biomechanical factor that accounts for individual differences in running economy. Significant variation in economy at a particular running speed occurs even among trained runners. So in general, improved running economy results from years of training and running with particular attention to specific movement patterns in running. Short-term training that emphasizes only proper technique of running probably does not necessarily improve running economy itself. Distance runners who lack an economical stride length pattern of their legs benefit from a short-term program of audio-visual feedback that also focuses on optimizing stride length. This is a good slide that kind of explains the energy expenditure and economy of walking versus running. Have you guys ever hit that point where you're so tired in a jog that you've just slowed down and you begin to walk, and then after a couple of minutes of walking, you almost feel like you're going just as fast as you were running, but you're actually walking? There's there's a point at which it becomes no longer economical to walk, and that's why it'd be more efficient and maybe a little bit easier to begin running at that point. So this shows the relationship between walking speed and oxygen uptake remains approximately linear between 3.0 and 5.0 kilometers per hour. As walking economy decreases at faster speeds, the relationship curves upward with a disproportionate increase in energy expenditure with increasing speed. This explains why, per unit of distance traveled, faster but less efficient walking speeds require more total calories expended per unit distance traveled. And so that's what's represented here. And at this juncture, running becomes more economical than walking. So that's what this first bullet point is saying here. There's the same total caloric cost when running a given distance at a steady rate VO2, whether it's a fast or slow pace. For horizontal running, the net energy cost per kilogram of body mass per kilometers traveled averages approximately 1 kilocalorie. The next couple slides discuss walking surface and how that affects efficiency and economy. If you have ever been for a walk on the beach, how many of you go down to that surface where the sand is nice and compact? And there's a reason that we do that, and that's kind of explained here in this slide. If you look at Table 8.6 in your Chapter 8, it summarizes the influence of terrain and walking surface type on the energy costs required of walking. Similar economies exist for level walking on a grass track or a paved surface. And not surprisingly, energy cost almost doubles walking in sand compared with walking on a hard surface. If you have grown up north and you were there for snow days, walking in soft snow, your metabolic cost increases threefold compared with treadmill walking. A brisk walk along a sandy beach or in freshly fallen snow provides an excellent activity for programs designed to burn calories or possibly improve physiologic fitness. For people who tend to gain weight during winter months, walking in snow is actually an excellent way to expend additional calories while still reaping the benefits of an intense aerobic workout. In regards to footwear effects, it requires considerably more energy to carry added weight on the feet or ankles than to carry similar weight attached to the torso. So if you've ever seen anyone walking around, they're carrying even weights in their hand. Think about the economy that's required of swinging your legs back and forth during your walking gait, or swinging your arms back and forth, again, while you're in motion in a walk. The closer you carry the weight to the center of gravity, the less energy is required to actually move that weight. So this is why ankle weights increase the energy cost of walking, almost comparable to the values observed for running. And this just exemplifies the different terrain effects on walking exercise economy. So you can see that there isn't much of a correction for walking on the sidewalk or a paved road, maybe a grass track. When you start to get into taller grass, like a plowed field maybe, there's a correction factor of 1.5. Hard snow that's compact, a little bit more than that, and then a sandy with maybe loose sand is a little bit more of a challenge, and therefore an increase in the kilocalories or the energy expenditure. So what about running then? Terrain, weather, training goals, the performer's fitness level, all influence running speed. And running energy expenditure can be quantified in two ways. During the performance of an actual activity in the ambient environment, so whether it's in a necessarily controlled climate or place, and it also can be quantified on a treadmill in a laboratory with concise measurements for speed, grade, environmental conditions. Energy expenditure will require increases if we don't maintain this efficiency of economy. So when we discuss becoming a better runner, and better running probably means reducing your times and therefore increasing your speed, a runner can increase their speed in 3 different ways. They can increase the number of steps in each minute, that's otherwise known as stride frequency. They can increase the distance between those steps, which is considered stride length, and then they can do a combination of those two by increasing their length and their frequency in regards to their stride. Well-trained runners run at a stride length that's selected through years of training. In other words, the body will naturally attempt to achieve this level of minimum effort of efficiency, and you basically run what's comfortable for you. There is no best style that exists that characterize elite runners and their stride length versus their stride frequency. You cannot do a mathematical formula and calculate that you need to take approximately 3 feet in between each of your steps to be the best runner. So this is something that, again, your stride as an elite level runner develops. Number one is something that comes automatically. It feels very natural. It's what's comfortable for the runner. But the way that we can coach is maybe to increase either the steps, the distance between the steps, or to maybe do a combination of the two. There are air resistance effects for runners. There are 3 particular factors that affect how air resistance manipulates the energy costs associated with running. Air density, the surface area of the runners themselves, in other words, how much body mass is present, and also the headwind of the velocity for itself. If you've ever seen cyclists draft, which is falling directly behind a competitor to counter the negative effects of that air resistance, to kind of save your energy costs, that is present with runners as well. Depending on running speed, overcoming air resistance accounts for 3 to 9% of the total energy requirement of running in even just calm weather. Running into a headwind creates an additional energy expense. In one study, running at almost 10 miles per hour in calm conditions produced 2.92 liters per minute of oxygen uptake. This increased by almost 6% to 3.1 liters per minute against a 10 mile per hour headwind, and to 4.1 liters per minute while running against the strongest wind, which was 41 miles per hour. So running into the strongest wind represents a 40% additional expenditure of energy to maintain running velocity. Swimming differs in several aspects from walking and running. The most obvious is that swimmers have to expend energy to maintain buoyancy while generating horizontal movement, at the same time using their arms and legs, either in combination or separately. Other differences include energy requirements for overcoming drag forces that impede movement of an object through a water medium. The amount of drag depends on characteristics of the water medium and the object's size, shape, and velocity. These factors contribute to a considerably lower economy swimming compared with running. More specifically, it requires about 4 times more energy to swim a given distance than to run the same distance. Energy expenditure has been computed from oxygen uptake measured by open circuit spirometry during swimming. In the pool, the researcher walks alongside the swimmer while carrying the portable measurement and gas collection equipment. This is not something that's done often, but it is an example of open circuit spirometry. And you can see here that the researcher is simply walking next to them to collect expired air for later analysis in the laboratory. So you can see here that there are 3 components that comprise the total drag force that slows down or impedes a swimmer's movement forward. And one of them is wave drag. And this is what's caused by waves that build up in front of and forms hollows behind the swimmer moving through the water. There was actually a lawsuit that occurred, I believe, in the last Summer Olympics where swimming was an event, some researchers did a study in regards to the success of the swimmers according to the lane that they had competed against. And they actually found that the way the pool was designed created a more advantage for individuals that were closer to the lanes on the exterior of the pool or on the outsides of the pool versus the interior lanes. And it was because of the drag that was created and how it splashed off the sides of the pool. It's also, another component is the skin friction drag, and this is what's produced as the water slides over the actual skin surface. So this is why you'll see swimmers that when they go into their tapering period, when they're close to a race, they'll actually shave everything. They'll shave their arms, they'll shave their back, they'll shave their stomachs. Male athletes will even shave their legs. And this is to slightly decrease the swimming energy cost and the physiologic demands during a swim race. There's also something called viscous pressure drag, and this contributes substantially to counter propulsive efforts of the swimmer at slow velocities. It results from separation of thin water sheet of water, which is called a boundary layer, adjacent to the swimmer. The pressure differential created in front of and behind the swimmer represents viscous pressure drag. Highly skilled swimmers who streamline any sort of stroke reduce this component of total drag. And streamlining with improved stroke mechanics can reduce the separation region by moving the separation point closer to the water's trailing edge. And this can also occur when an oar slices through the water with the blade parallel rather than perpendicular to the water movement. This particular graph shows oxygen uptake for 2 elite and 2 trained swimmers during 3 competitive strokes. They did the breaststroke, the back crawl, and also the front crawl. There were some interesting outcomes in regards to this study. They actually measured 2 elite and 2 trained swimmers during the different strokes that we just mentioned. What they found was that elite swimmers swim a given speed with a lower VO2 than the untrained skilled swimmers. They discovered that breaststroke costs most at any speed and represents the least economical of the different strokes, followed up by the backstroke. And this particular study said that the front crawl is the least expensive, most economical mode among the 3 strokes. And it kind of makes sense, ladies and gentlemen, if you consider which one of those typical strokes seem to be most challenging. I would definitely say the backstroke, the breaststroke would be difficult, followed by the backstroke. Front crawl makes sense that it might be the most economical mode because you're not panting when you're having to do that particular stroke. But that's just personal preference for me. Some of you might find it easier to perform the breaststroke or the backstroke. That is our lecture for Chapter 8. Again, these are the most important parts coming out of the particular sections for Chapter 8, Part 1 and Part 2. Go over them at your own time, and thanks for listening.